Geothermal well stimulation is different from what you have seen so far. The system is no longer a container. It is an energy system. The objective is not storage. It is heat extraction. Fluid is circulated through hot rock. Heat is transferred. Energy is produced. This makes circulation critical. Without flow, there is no energy. The system operates at high temperature, typically between 100 and 300 degrees. At these conditions, fluid behavior changes, rock behavior changes, and materials degrade faster. So the focus shifts. You are not just improving permeability. You are improving circulation, enhancing heat transfer, and increasing energy output. And this is not a one-time treatment. Geothermal stimulation is continuous. You assess the system, treat the limitation, maintain performance, and monitor over time. Final idea: geothermal is not a treatment. It is a system you must continuously manage. Geothermal performance is not limited by a single factor. It is constrained by several processes acting at the same time. The first limitation is permeability. If the fracture network cannot carry enough fluid, there is no effective circulation. And without flow, there is no heat extraction. The second limitation is mineral scaling. Silica, calcite, and sulfates deposit continuously during operation. They gradually block fractures and reduce flow capacity over time. This damage does not occur before the system runs. It develops during operation. The third limitation comes from thermal effects. Temperature cycling changes the rock over time. It can create new pathways, but it also introduces instability. So the system is constantly evolving. This changes the objective. You are no longer focused on pressure or production rate. You are focused on energy output. To achieve that, 3 targets must be managed. You must increase permeability, improve circulation, and maximize heat extraction. The type of system also matters. In hydrothermal systems, natural permeability already exists, so the goal is to optimize flow. In enhanced geothermal systems, permeability is low or absent, so it has to be created. In fractured rock systems, some structure is present, but connectivity must be improved. The mechanism itself is simple. Cold fluid is injected. It flows through hot fractures, absorbs heat from the rock, and returns to the surface as hot fluid. The key control point is circulation efficiency. Flow determines how much heat is recovered, and permeability controls that flow. Temperature adds another layer of complexity. At high temperatures, fluids degrade, scaling increases, and rock properties continue to change. This is not a stable system. It evolves as it operates. Final principle. If flow is restricted, energy is lost. Performance loss in geothermal systems is not random. It follows clear physical mechanisms. The first is scaling. As temperature and pressure change, minerals begin to deposit. Silica, calcite, and sulfates build up within the fractures. Over time, these deposits restrict flow. Circulation becomes weaker, and energy output declines. The second mechanism is thermal stress. Cold fluid is injected into hot rock. This creates temperature differences, and the rock responds. It contracts, and small fractures begin to form. This can increase permeability, but it also introduces instability. Flow paths start to change, and the system becomes less predictable. The third mechanism is fluid-rock interaction. At high temperatures, chemical reactions become more active. Some minerals dissolve, while others form and accumulate. As a result, permeability evolves over time, and it does not always improve. These mechanisms do not occur separately. The system changes as it operates, not before, but during. The response must be specific to the limitation. If scaling is the issue, chemical treatment is used to remove deposits and restore flow. But scaling will return. This is maintenance, not a permanent solution. If permeability is insufficient, hydraulic stimulation is applied. Fractures are created or extended to improve circulation. This is essential in systems with little or no natural permeability. But it comes with risk. You are changing the stress field, and that can trigger seismic events. There is also a thermal approach. Cold fluid is used deliberately to create fractures through temperature contrast. This avoids chemicals and high pressure, and allows the system to stimulate itself. Each method targets a different problem. Scaling requires chemical removal. Low permeability requires hydraulic stimulation. Limited connectivity can be improved thermally. Final principle. You are not applying generic treatments. You are correcting the mechanism that limits the system. Geothermal systems are not forgiving. If constraints are ignored, control is lost. One of the main challenges is scaling. You can remove deposits, but they will return. That is part of how the system behaves. Over time, flow declines again. This is not a failure of the treatment. It is the natural behavior of the system. Another risk is fracture instability. As pressure increases, fractures expand. But they do not always grow where you expect. Flow paths can shift, faults may be activated, and seismic responses can occur. Thermal degradation is also constant. High temperature affects everything. Fluids begin to break down, and materials lose strength over time. This has a direct impact. Treatments do not last as long. Equipment life is reduced. System reliability declines. These effects define the operating limits. Temperature remains high, typically between 100 and 300 degrees, and many conventional fluids cannot perform under these conditions. Corrosion becomes more aggressive, so material selection becomes critical. Every component in the system must be able to withstand heat. Standard materials are often not sufficient. Pressure must also be controlled at all times. If pressure increases too far, fractures can grow uncontrollably, and the system becomes unstable. This is a constrained system. Every decision must stay within limits. Final rule: do not optimize aggressively. Operate within boundaries. Final principle: control is maintained by respecting those limits. Geothermal systems are not solved with a single treatment. They are managed over time. Performance does not decline because of one failure. It declines because the system keeps changing. Scaling builds up. Fractures evolve. Materials degrade. So the response cannot be aggressive. It has to be systematic. You start by understanding what is limiting the system. It may be scaling. It may be restricted flow. It may be poor connectivity between fractures. Once the limitation is clear, you apply the appropriate treatment. Scaling is addressed chemically. Flow limitations are improved through hydraulic or thermal methods. But treatment alone is not enough. The result must be maintained. Operating conditions need to be controlled to prevent rapid decline. At the same time, the system has to be monitored continuously. Performance trends must be tracked. Changes must be detected early. Future interventions must be planned in advance. This cycle does not stop. This is not maintenance in the traditional sense. This is how the system operates. The common mistake is to treat geothermal like oil and gas. Solve the problem once, and move on. That approach does not work here. Performance drops again. Efficiency declines. Energy is lost. A control approach is different. You do not chase problems. You manage the system. Final principle: assess, treat, maintain, and monitor. Final line: you do not finish geothermal. You run it. Geothermal systems are fundamentally different from oil and gas. They operate under different conditions, with a different objective and a different way of working. Start with the environment. Geothermal systems operate at high temperatures, often between 100 and 300 degrees. At these conditions, standard fluids do not perform as expected, and conventional materials degrade more quickly. So temperature becomes the primary design constraint. The objective is also different. In oil and gas, the goal is to increase production. In geothermal systems, the goal is to extract heat. Permeability still matters, but for a different reason. In oil and gas, permeability creates flow to the well. In geothermal systems, it enables heat transfer between the rock and the fluid. That changes the role of fractures. In oil and gas, fractures are pathways to the well. In geothermal, they act as surface area for heat exchange. The way the system operates is also different. Oil and gas wells are often treated once and then produced. Geothermal systems continue to change during operation. Scaling builds up, flow declines, and the system must be managed continuously. This also introduces additional constraints. Higher pressure increases risk. Fractures may grow beyond the intended zone, and seismic activity can become a concern. So although the tools may look familiar, the system is not. Different conditions, different objectives, and a different approach to operation. Final principle: if you apply oil and gas thinking, performance declines. If you adapt to the system, you maintain control. Now bring everything down to decisions. Flow is the starting point. Without flow, there is no energy. Permeability directly controls output. Scaling is always present. It cannot be eliminated. It has to be managed continuously. Hydraulic stimulation defines the system. Without fractures, there is no circulation, and without circulation, the system cannot produce energy. Temperature affects every part of the system. Fluids behave differently. Rock properties change. Materials degrade over time. The system does not remain stable. Fractures evolve. Materials weaken. Performance gradually declines. This is not a one-time treatment. It is continuous operation. So the approach must stay systematic. You assess the system. You treat the limitation. You maintain performance. And you monitor continuously. Final principle: control the flow, control the heat, and you control the system. Step back and look at the system as a whole. Geothermal is not a well. It is not a one-time treatment. It is a system that you operate. A common mistake is to approach it like oil and gas. Fix the problem. Increase performance. Move on. That approach does not work here. Flow declines again. Scaling returns. Energy output drops. A control approach is different. You do not fix geothermal. You run it. You do not chase individual problems. You manage system behavior. Scaling is expected. System changes are expected. Performance decline is expected. And all of it is controlled over time. This is where the difference appears. Two engineers can work on the same reservoir, using the same tools. One reacts to problems as they appear. The other manages the system continuously. One loses efficiency. The other sustains energy production. The difference is not experience. It is discipline. Final principle: success does not come from doing more. It comes from controlling the system over time. Final line: run the system, or the system runs you. 4 different systems. 4 different constraints. Hydrogen is defined by containment. Carbon dioxide storage is limited by pressure. Carbon dioxide acidizing depends on reaction control. Geothermal systems are governed over time. They are different in application, but they follow the same principle. Containment, pressure, reaction, time. These define how the system behaves and how it must be controlled. The common mistake is always the same. Trying to maximize the outcome. More flow, more pressure, stronger reactions, higher output. That approach leads to failure, because maximization removes control. The correct approach is different. You do not control the output. You control the system, and the outcome follows. Final line: if control is lost, the system is lost.